Hello my dear students. So in my last class, I was explaining about the applications of periodic properties. So there we studied about the electropositive or metallic character of the elements which are present in the periodic table, and also the electronegative or non-metallic character of the elements. So how these electropositive and electronegative character of the elements is observed in the periodic table is understood. So with the increase in the ionization energy, non-metallic character increases, and with the decrease in the ionization energy, metallic character increases. So this is what so we understood by studying the electropositive and electronegative character of the elements, and also how the variation of metallic and non-metallic character in the periodic table is observed. So as the ionization energy values decreases on descending a given group, the metallic character of elements increases and non-metallic character decreases. And as we know that the ionization values increases on moving from left to right in the period, the metallic character of the elements decreases. On proceeding from alkali metals to halogens in a given period, the non-metallic character goes on increasing. That is, alkali metals are metals and halogens are non-metals. And next we understood how the variation of ionic or covalent radius in the periodic table is observed. So the size of the atoms increases on moving down the group because the number of principal shell increases on moving down the group, and distance between the nucleus and outermost electron shell increases. So that is why, so what happens is, so the effect which is caused by the increase in the effective nuclear charge is lesser than the effect which is caused by the increase in number of principal shells. So due to this reason, the covalent radii goes on increasing. And next we understood about the oxidizing and reducing properties. On moving along a period, electron affinity value increases, so the addition of electron will become much more easier. So the elements undergo reduction or they act as good oxidizing agents. In the periodic table, that especially group 17 elements, which are called as halogens, are good oxidizing agents. Similarly, on moving down the group, ionization energy value decreases and the elements can lose their outermost electrons very easily. So they act as good reducing agents. Lithium is the strongest reducing agent in aqueous solution because it can lose its outermost electron easily and forms unipositive cation. So this is where we stopped in our previous class. And in this session, so a very interesting topic is going to be discussed, so which is called as effective nuclear charge. The effective nuclear charge, often it is symbolized as Zeff or Z, is the positive charge which is experienced by an electron in a polyelectronic atom. The term effective is used because the shielding effect or negatively charged electrons prevents higher orbital electrons from experiencing the full nuclear charge of the nucleus due to the repelling effect of inner layer electrons. The effective nuclear charge experienced by an electron is also called as the core charge. It is possible to determine the strength of the nuclear charge by the oxidation number of the atom. Most of the physical and chemical properties of the elements can be explained on the basis of electronic configuration. Consider the behavior of ionization energies in the periodic table, and it is known that the magnitude of ionization potential depends upon size of atom, the nuclear charge, the screening effect of the inner shells, and also the extent to which the outermost electron penetrates into the charge cloud set up by the inner lying electrons. So this is all about the introduction of effective nuclear charge. So as I said, the electrons residing in the shells between the nucleus and valence shell are called as intervening electrons. So those electrons which are present in between the nucleus and the outermost electron, so they are called as intervening electrons. These electrons reduce the force of attraction between the nucleus and the outermost shell electrons. The reduction which is produced in the force of attraction due to the presence of intervening electrons is called as shielding effect or screening effect. With the decrease in the force of attraction caused by shielding effect, the actual nuclear charge is decreased by a quantity, so which is symbolized as sigma, and which is also called as a screening constant. So sigma is called as a screening constant. The decreased nuclear charge will be equal to Z minus sigma, and this is what is called as effective nuclear charge. Okay, so this is how. So the decreased nuclear charge will be equal to Z minus sigma, and this is called as effective nuclear charge, and it is symbolized as Z effective. So the effective nuclear charge, that is Z effective, is defined as the actual nuclear charge minus, so this is the actual nuclear charge, and actual nuclear charge will be always equal to the atomic number. So atomic number of the element is nothing but the actual nuclear charge which has been possessed minus the screening constant. So screening constant is sigma, produced by electrons residing between the nucleus and the outermost shell electrons. So now let us understand the Slattus rule for calculating Z effective and sigma. So Z effective is nothing but the actual or the effective nuclear charge, and sigma is the screening constant. The value of sigma for electron residing in an ns or any one of the np orbital of nth shell of an atom or an ion is the sum of the following contributions. So each of the remaining electrons in the nth shell makes a contribution of 0.35 to the value of sigma. Okay, so you should keep it in your mind. So all these points to calculate the effective nuclear charge felt by the last electron of any element. So usually, so each of the remaining electrons in the nth shell makes a contribution of 0.35 to the value of sigma, and each of the electrons in the n-1th shell will make a contribution of 0.85, and each of the electrons in the next inner shells make a contribution of 1, and there will be no contribution to the value of sigma by the electrons which are residing in the orbitals having higher values of their principal quantum numbers than the orbital containing the electron for which sigma is to be calculated. And if sigma is to be calculated for an electron of 1s orbital, there will be a contribution of 0.30 from other single electron in the 1s orbital. And next, so the value of sigma for an electron which is residing in n-1 d orbital of an atom or an ion is the sum of the following contributions. There will be no contribution to the value of sigma by the electrons residing in ns orbital, whereas each of the remaining electrons in the n-1 d orbital makes a contribution of 0.35 to the value of sigma, and each of the electrons in the inner s and p orbitals and inner shells makes a contribution of 1.0 or 1. So it will make a contribution of 1. So now let us take up some examples and calculate the effective nuclear charge so that we can understand the Slattus rule in a better way. So here the first problem says that calculate the effective nuclear charge felt by the last s electron of sodium. So the atomic number of sodium is 11. So very first what we have to do to calculate our effective nuclear charge is so write down the electronic configuration of sodium. So the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. So now according to the Slattus rule what we have discussed just now, so here, so for this that is nth shell which is present, so we have a contribution of 0. So that is so there will be no contribution to the value of sigma by the electrons residing in the orbitals having higher principal quantum numbers. So this is higher principal quantum number. So for this we will not have any contribution for the value of sigma. So that is why 0. And since it is present in the nth shell, so this is a nth shell, that is principal quantum number. So the first principal shell which is present, so that is why the contribution will be equal to 0.35. So 0 into 0.35. Now let us move on to the next shell, that is 2s2 2p6. So here we have 6 plus 2 8 electrons, and this is a n minus 1 shell. So this is n minus 1th shell. So that is why this will contribute 0.85. So since there are 8 electrons present, so 8 into 0.85. And this is the last one, so 3s1. So here we are having only one electron which is present in the outermost shell. So that is why this will give 1 into 2. Okay, so 1 into 2. So that is because since this is the outermost shell, so what and all the electrons which are residing, so we have to leave these electrons because these are the intervening electrons. With respect to this 3s1 electron, so 2 electrons are present, that is 1s2, 2 electrons are present, so 1 into 2. Now what we have to do, we have to sum up all the values and calculate sigma. So what we are going to get, so we are going to get 8.8. So 8.8 is the value of sigma, that is a screening constant. So now we have Z actual, so that is the actual effective nuclear charge, so that will be equal to the atomic number of the element. So atomic number of sodium is equals to 11 minus sigma, so the value of sigma is 8.8, 11 minus 8.8, which is equals to 2.2 or 2.20. So this is the effective nuclear charge which is felt by the last s electron of the sodium. Similarly, so this is another example. So here they have asked us to calculate the effective nuclear charge felt by the last p electron of oxygen, and the atomic number of oxygen is equals to 8. So just like how we have solved for sodium, so we have to write down the electronic configuration of oxygen, and the electronic configuration of oxygen is 1s2, 2s2, 2p4. Okay. So now we will calculate sigma. So for this 1s2, so since this is a principal quantum number, so how many electrons are there? So leaving up the outermost electron, so we have 4 plus 2 is 6. So we are calculating the charge felt by the last p electron, so that is why 5 electrons are left here. Okay, so 5 into, so since this is in the nth shell, we have 0.35. Okay, 0.35 plus so 2 into 0.85. So this is because so if we leave this shell, we have 2 electrons left here, 1s2, 2 electrons are left, and this is n minus 1th shell. So the value for n minus 1th shell, or the each of the electrons in the n minus nth shell makes a contribution of 0.85. Since we have 2 electrons, 2 into 0.85. Now sum up this, we will get 3.45. So now we know the actual effective nuclear charge or the atomic number of oxygen, that is 8, and screening constant sigma is 3.45. 8 minus 3.45 is equals to 4.45 is the effective nuclear charge felt by the last p electron of oxygen. So there are another 2 problems in the textbook, you can go through it, and if you don't understand, definitely once the offline classes starts, we will have a revision on solving the problems to how to calculate the effective nuclear charge felt by the different electrons which are present in the valence shell of various different elements. So now moving on to the applications of Slattus rule. So the first application says that, so 4s orbital fills first than the 3d orbital. So we can give a justification for this, how the 4s orbitals will fill first than the 3d orbital. Suppose in the case of potassium, so the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So to this, if I have to calculate the screening constant means, so here, so since we have only one electron which is present in the outermost shell, so for this, so we will not find any electrons. So that is why for nth shell, we will have 0.35 into 0. And n minus 1th shell, we have 8 electrons, and 6 plus 2, 2s2, 2p6, 8 electrons we have. So these 8 electrons will contribute 0.85, that is because this is n minus 1th shell. Plus, so for this, for s1, we have 10 electrons which are present here. So that is why 1 into 0 into 10, which is equals to 16.80, is the screening constant of this particular element. Now we will say, or we will calculate the Z effective. So Z effective is equals to 19 minus 16.80, which is equals to 2.20. Suppose if the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, so then the screening constant will be equal to 0.35 into 0 plus 1.0 into 18, which is equals to 18, and Z effective is 1. So this value is lower than the previous one, that is, so this value, this is 2.20, this is 1. So since it is a lower value than the previous one, in which the last electron enters into the 4s orbital, so the electron always prefers the 4s orbital than the 3d orbital. So in this way, the Slattus rule helps us to understand how the 4s orbital will fill first than the 3d orbital. And another important application of this Slattus rule is so the formation of cation in the transition metals. So during the formation of transition metal cation, electron removal takes place from the outermost s orbital and not from the d orbital. For example, during the formation of Mn2 plus, electron remove from 4s orbital and not from the 3d orbital. So now let us see with the help of Slattus rule how we can justify this statement. So the electronic configuration of manganese is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. And if the electron is removed from 3d orbital, then the effective nuclear charge observed by the outermost electron of this manganese will be equals to, so here the Z actual will be equals to 25 and the screening constant is equals to 19.40. So we'll get, so the effective nuclear charge is 5.60. The effective nuclear charge, suppose if the electronic configuration of manganese is like this, that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. That means, so suppose the electron has been removed from the outermost s orbital, so what will be the configuration or effective nuclear charge of this particular manganese? So then the screening constant will be equals to, so 1 into 0.35, 13 into 0.85, 10 into 1.0, which is equals to 21.40. Now let us calculate the Z effective, which is equals to Z actual minus screening constant, 25 minus 21.40, which is equals to 3.60. So here the effective nuclear charge felt by the 4s electron of manganese is equals to 3.60. This value is lower than the effective nuclear charge felt by the 3d electron of manganese. So what happens is the removal of electron is easier from the 4s orbital than the 3d orbital. So in this way we can use the Slattus rule to justify the formation of cation in transition metals. That is, so during the formation of transition metal, that is electron removal takes place from the outermost s orbital and not from the d orbitals. So this completes the periodic properties, that is which we have started long back, unit 4, chapter 4.3. We have come to the end, and in my next class, so we will start with the organic chemistry part. Okay, so if you have any doubts regarding the Slattus rule for calculating Z effective and screening constant, and also how to solve the problems, so we will do it in the offline classes. Thank you, dear students.